Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we are continuing with our investigation of carbohydrates. Last lecture, we discussed the distribution of product in the cyclization of the glucose Fischer projection. That is, why did we get different amounts of alpha D-Glucopyranose and beta D-Glucopyranose? Beta D-Glucopyranose was observed to predominate to the amount of 64%. Now this distribution could only be rationalized if we converted the Haworth projection formula into the chair conformers. And these are the chair conformers we drew last time. For alpha D-Glucopyranose, we were able to draw structures A and B. Now structures A and B are just different ring flips of the same chair conformer. And so we compared structure A and B in order to determine which one was the major or most stable chair conformer. The assumption was that large groups in equatorial positions was more stable than when it was axial group positions. Structure B had more large groups, the OHs and CH2OHs, more large groups in the equatorial position. Hence, it was the more stable chair conformer. We then repeated the process for beta D-Glucopyranose. When we drew both chair conformers and compared them, we found that structure D had more large groups in the equatorial position and hence was the more stable chair conformer. Then in order to explain the percentage distribution, we compared chair conformer B to chair conformer D. We found that when you formed beta D-Glucopyranose, you could get to a chair conformer where all of the large substituents, all of the OHs and the CH2OH were equatorial. Whereas in alpha D-Glucopyranose, one of the OHs was axial. This produced a little larger repulsion and hence caused structure B to be slightly minor, a little higher energy, a little harder to form. Now, I repeat this because it is worthwhile to note that this type of interpretation doesn't always work. We want to repeat this for the structure mannose. In order to do that, I need to make a little room and we need to draw mannose. How does mannose differ from glucose? So I want to convert these structures so I don't have to draw them all again. I want to convert them to the structure for mannose. So I'll erase these names. And we want to convert our glucose molecule to mannose. Now to understand how to change the Haworth, we need to draw a Fischer. So I'm going to draw in red, just so it stands out. D-Mannose. Okay, so there is D-Mannose. Now when D-Mannose cyclizes, this OH right here will be required to make a 6-carbon ring. That is, this is carbon 1, that's carbon 2, carbon 3, carbon 4, carbon 5. Now carbon 5 carbons and 1 oxygen create a 6-membered pyranose ring, so this oxygen will cyclize. So I can redraw this, okay, and I will attempt to do that in the limited amount of space I have here. very limited space. And so there's an OH here. Above that, there's an OH. Another OH. And then I have my anomeric carbon that forms where the OH can be on either side. OH alpha is on the same side as the reference. Here is my reference. So the OH for alpha. So let's start with the alpha. It's there. So here's the Fisher projection. Now don't forget, I'm going to just put some dots. This position, and this position, and this position are not carbons. Okay? In line formulas, vertices are often carbons. What I'm doing is I'm just stretching the two bonds. This is a single bond here, and this is a single bond attaching here. So don't get confused. Those black dots are not carbons. Now, convert this to this Haworth. Imagine that we're going to change this Haworth for alpha D-Glucopyranose to the mannose using our standard rules. Remember, the OH that is right is below, the OH that is left is above. So this OH is correct. OH that is right is below. This OH is wrong. It should have been above. It's that guy. That OH is left, so it's above, so that one's correct. This OH is right, this is below. And in a D sugar, the CH2OH is up. So I see the only change I have to make in my Haworth, based on this Fisher, is to switch this OH right here. So let's erase this. Now that I know the change I have to make, I can clear this up because it's a little cluttered. And I can begin changing my alpha D-Glucopyranose into mannose. So all I have to do is change that one OH. So let's do that. This OH should be up. That single change changes this molecule from alpha D-Glucopyranose to alpha D-Mannopyranose. Of course, I'm running out of room. Okay. So I just have to change that OH. That is this position and that position. So if I switch that, this becomes an OH. And here, this becomes, let's give us a little more room, an OH. Now let's do the same thing for beta D-Glucopyranose. Again, remember it was this OH right here that we had to change. So let's do it. With that OH up is beta. This is beta D-Mannopyranose. And so the OH that switches is this one. And they're the two chair conformers for the beta D-Mannopyranose. So let's look at the alpha first, the alpha D-Mannopyranose, and look at both ring flipped structures, structures A and B. Structure A, if I was just doing a simple comparison, would yield 2 OHs equatorial, 2 OHs, and 1 CH2OH axial, so 3 large groups axial. In structure B, we have only 2 large groups axial. Less axial groups, less large groups axial, means less repulsion, means it's energetically more favorable. Remember, putting the large groups equatorial produces a more stable chair conformer. Okay, so B, between A and B, is more energetically favorable. Now let's go to beta D-Mannopyranose, and let's compare C and D. In structure C, again, I have 1, 2, 3 OHs axial, 1 CH2OH axial, only 1 OH is equatorial. If I go to D, 4 groups are equatorial, 1 axial. D would reduce the repulsive force the most. Okay, because it has the most groups equatorial, most large groups equatorial. Now, compare structures B and D for mannose. If we do this comparison in the same way we did the glucose scenario, we would say the same thing. Structure B has 2 axial OHs. Structure D only has 1. More of the large groups are equatorial in structure D. Structure D is more energetically favorable, hence beta D-Mannopyranose should predominate. What's interesting is that it is known that alpha D-Mannopyranose predominates over beta D-Mannopyranose. The question is, why? Well, there is another repulsive effect that we haven't discussed. The molecule has to be in the proper orientation for this new effect to take place, and hence it's very hard to predict. It doesn't occur in the glucopyranose case. But in the mannopyranose case, the lone pairs of the oxygen on the ring here and the OH oxygen lone pairs here produce electron repulsion. Now, if you look at structure B, since the OH has gone axial, is well removed, that electron-electron repulsion has been removed. Now, in the case of mannose, this repulsion is so great, it causes D to be energetically less favorable. So let's recap. Based on our simple premise of more equatorials being stable, structure D looks like it's more favorable. But because of this hidden electron-electron repulsion, that reverses that in the case of mannose. Note it doesn't do that in the case of the previous glucose, so we didn't consider it. Because the OH has moved to the axial position in the alpha D-Mannopyranose, structure B, it's moved far away from the lone pairs. It's down here, which means that repulsion has been removed. In this case, that reduces the repulsion in the molecule, and B becomes a more favorable structure, and hence alpha D-Mannopyranose predominates. This effect is known as the Anomeric Effect. The anomeric effect is a repulsive force caused by the oxygen of the ring and the OH of the anomeric carbon. When this repulsive force is great enough, it will often cause what you would predict to be the less stable, less major sugar to become major because it's minimized. The anomeric effect is a repulsive force, an electron-electron repulsion between the anomeric hydroxyl and the oxygen of the ring. You cannot predict when it's going to occur, and you're not expected to. I only expect you to know it for the case of the D-Mannopyranose. I'm giving you this information in case you do continue in biochemistry courses, you will be running across this anomeric effect. But it's very difficult to predict when it will occur. So only apply it for this specific example. You only need be able to draw structures B and D and compare them. Okay. Let us continue and return to our examination of D-glucose. And this time look at the two forms of D-glucose. Here is alpha D-Glucopyranose. And over here I'll draw beta D-Glucopyranose. Now, what's interesting is you can actually isolate these two different sugars because they are diastereomers. They have different physical properties. If glucose is recrystallized below 80 degrees, you can isolate alpha D-Glucopyranose. It has a melting point of 146 degrees Celsius. And I'm not going to make you know that. And it has a specific rotation. Remember, square brackets around alpha means specific rotation of plus 112 degrees. Now, you can take this pure salt and redissolve it in water. What's interesting is it converts to a specific rotation when you dissolve it in water of plus 52.6 degrees. Interesting. You can also isolate beta D-Glucopyranose in pure form. If you recrystallize it from water impurity and above 100 degrees Celsius, you get beta D-Glucopyranose. And it has a melting point of 150 degrees Celsius. Remember, diastereomers have different physical properties. And its specific rotation is plus 18.7 degrees. What's interesting is if you take your pure form, okay, let's write the names. This is alpha D-Glucopyranose. And this guy is beta D-Glucopyranose. Okay, now If you take the beta D-Glucopyranose and dissolve it in water, it also very slowly converts its specific rotation from plus 18.7 to plus 52.6. This change in specific rotation over time when the pure compounds are redissolved is called mutarotation. Okay, let's say that again. We isolate alpha D-Glucopyranose in pure form. We measure its specific rotation as plus 112. We then redissolve it in water. And over time, we slowly watch the specific rotation convert to plus 52.6. That change in optical rotation is what we call mutarotation. Likewise, if we take pure beta D-Glucopyranose, measure its specific rotation, it's plus 18.7. Dissolve it in water and observe it over time, that plus 18.7 slowly changes to plus 52.6. The change in the optical rotation is mutarotation. But what causes it? What causes it is the equilibrium. The equilibrium to the open chain form, which is present 0.02%. And that produces, the open chain form then converts between alpha and beta. It is the equilibrium I'll have to shorten this arrow. And I'm going to use a squiggle. If you see a squiggle, what a squiggle means is you don't know the stereochemistry, or that there's some equilibrium between the OH being up and the OH being down. So the anomeric carbons OHs get scrambled. Now we know that happens in water. We know that if you dissolve one of these sugars in pure form in water, the hemiacetal can open up, that there's 0.02% open chain form. But the open chain form can close again, and when it closes, it could reform the alpha, or it could convert to beta. Because there's only 0.02%, this conversion is very slow. Now, what happens if you let these pures slowly convert is you end up forming a 36% alpha, 64% beta mixture. We know that. This is what I'm representing with the squiggle. The squiggle means I don't have pure alpha or pure beta, but what I have is a mixture, some mixture. And that's what the squiggle means. All right, now, let's see if I can make that stand out a little better. There we go. So, why 52.6? Well, the answer is pretty easy. What happens if you take 36% of 112, so 0.36 times 112 degrees, and you average that, add that with 64%, 0.64 times 18.7. And what you realize is you get 52.6 degrees. 52.6 degrees is just the average rotation obtained from the equilibrium mixture. Mutarotation is not the equilibrium. Mutarotation is the conversion of the optical rotation from plus 112 to 52.6 or plus 18.7 to 52.6. But mutarotation is caused by the equilibrium. So whenever you take pure alpha D-Glucopyranose and dissolve it, or you take beta D-Glucopyranose and dissolve it, the hemiacetals can open up and you can get this conversion. Okay. What's interesting, though, is that you can stop this open up equilibrium, the conversion to the fissure, the production of the open chain, if you take your hemiacetal and you convert it to a full acetal. So let's start with alpha beta D-Glucopyranose. And let's react this with methanol and anhydrous HCl. Now you recall methanol and anhydrous HCl would react with aldehydes to produce hemiacetal. But the acid could protonate a hydroxyl in the hemiacetal, and you could lose water and produce there's an H there, of course, the carbocation. Then methanol could attack. Note, for simplicity purposes, I'm going to draw it the same way. But the carbocation's trigonal planar. Remember, carbocations are sp squared, and the methanol could attack either side, which means the OCH3 will not necessarily be pointing down. It's probably best represented by a squiggle, but I'm going to just draw it the same way. Okay? And I'm going to run out of room. Let's put OCH3 here. Okay. Well, maybe I won't. There we go. And it still has an H on it. And so if we now kick out H+, we produce this. Now note, compare this molecule to our original alpha D-Glucopyranose. Okay, so let's put the name here. Alpha D. Alpha D-Glucopyranose was a hemiacetal. Why? Well, the anomeric carbon right here has two oxygens attached to it. That means it's in the family hemiacetal, acetal, ketal, hemiketal. Singly bonded oxygens. There is an OH off of it, so it's hemi. And as it's the line formula, we know there's an H here, so that means aldehyde, so that's a hemiacetal. Come over here now. Our anomeric carbon still has two oxygens bound to it, so it's in that family. Two oxygens singly bound. But there's no OH, so it's not hemi. There's still an H, as indicated by the line formula, but because it's not hemi, it's a full acetal. This is a hemiacetal. But this one is a full acetal. What's the difference between hemiacetals and full acetals in solution? Well, one major difference is, remember, alpha D-glucopyranose undergoes mutarotation. You dissolve it, it opens up. Full acetals do not. They're stable in solution. In basic solution, you have to throw them in acid to convert them back to the hemi and get the ring opening process. So if you had this type of molecule, it would not undergo mutarotation. How would you name something like this? Well, this bond, the OCH3 bond, is called a glycosidic linkage. Glyco-cidic. It's actually one word, no hyphen, but I have no space. It's a glycosidic linkage. Because of that, when you make the full acetal, you convert the OS sugar to an oside. So I'm going to write the name down here. And my alpha D, in this case, I've drawn, my alpha D-glucopyranose has become alpha D-glucopyranoside. The substituent, though, the alcohol you reacted with, you could use different alcohols. You could have, instead of methanol, you could have used ethanol, in which case, instead of the CH3O, you'd have an ethyl group on the O. Clearly, we need some way of identifying what is the group off the oxygen. And we do this by writing the name of the alkyl group, methyl, as a separate word out front of oside. So whenever you see oside, you need an alkyl written out front. And this is methyl alpha D-glucopyranoside. So what this name tells you when there's oside, it tells you the OH in alpha D-glucopyranose, the OH off the anomeric carbon, has been replaced with some kind of alkyl. And the name of that alkyl is located here. And so draw alpha D-glucopyranose, you can correct when you are given alpha D-glucopyranoside by just dropping the H and replacing it with an alkyl for the OH off the anomeric carbon. Okay, and that's it for glycosides. We have one more thing I'd like to look at. With the glycoside chemistry, you notice we've started looking at reactions. We've started looking at the reactivity of the sugar. And there is one more thing about this reaction before we leave it that I guess I should answer. That is why did we attack or substitute for the OH on the anomeric carbon? There's a lot of OHs in this sugar. Why did the OCH3 not replace one of the other OHs on the alpha D-glucopyranose? And the answer has to do with the carbocation. The carbocation is especially stable because of the oxygen. It's next door to the oxygen on the ring. I can dump in 2 lone pairs. If I do that, I resonance stabilize my carbocation. So there is a resonance contributor helping stabilize this carbocation. If you replace any of the other OHs and produce a carbocation, you do not get this resonance structure. If you put the plus here, here, or here, it's too far removed. And so this is the only carbocation that is resonance stabilized. Hence it's more energetically favorable, hence substitution occurs in this position. All right? Let's press on with reactivity and begin looking at oxidation. Of monosaccharides. We'll introduce this in this scribblecast, but finish it off next scribblecast lecture. Saccharides. Okay. Oxidation of monosaccharides. Now, last semester we learned that aldehydes are more easily oxidized than alcohols. That is, you can actually take an aldehyde and you can oxidize it very readily to the corresponding carboxylic acid. Now, when you used alcohols and did this process, alcohols required much more powerful oxidizing agents. But they did go through the aldehyde. So last semester we learned that if you oxidize an alcohol, the oxidizing agents you used for the alcohol had to be more powerful, but they did go through the aldehyde. You learned that the primary alcohol converted to a carboxylic acid via the aldehyde. And you couldn't stop it easily at the aldehyde because the aldehyde was more easily oxidized. Well, it turns out that the oxidizing agents that can be used to oxidize an aldehyde to carboxylic acid are very mild oxidizing reagents. Our oxidizing reagents can be silver with 2 ammonias attached to it, plus in hydroxide base. You could use copper citrate, which overall is 2 minus in hydroxide solution. Or you could use copper tartrate. In base solution. Now, the silver reagent is called Tollen's reagent. The copper citrate is called Benedict's. And
And you need to know these names.
Reagent.
And finally, copper tartrate in base is called Fehling's. Fehling's reagent. So there you have the three oxidizing agents that can be used. Now what's interesting is whenever you do an oxidation, the agent that does the oxidizing gets reduced. That is, the aldehyde actually reduces it. So for example, if I use Tollen's reagent, and I'll just write Tollen's, I will produce the carboxylic acid. Now note one very important point. All these reagents are base. What happens to an acid in a base? The acid gets deprotonated, so the CO2H becomes a CO2 minus. And the silver plus will become silver solid. So the aldehyde reduced the metal. The metal oxidized the aldehyde, but the metal itself gets reduced. Now, note, our sugars, okay, let's take glucose, are aldehydes. Yes, in hemiacetal form they aren't. When they're in pyranose rings, they're not. But the open chain form is an aldehyde. And whenever you dissolve the hemiacetal in water, you get a small amount of the open chain form, which can react. So here's D-Glucopyranose. If I react it with Tollen's reagent, what happens? Well, this aldehyde group becomes a CO2 minus. Now, if I use Tollen's reagent, I'll get silver metal. What if I use Benedict's reagent? Well, if I use Benedict's or Fehling's reagent, I would produce copper solid. So the aldehyde, the sugar, reduces the reagent. Now, sugars that do this are therefore called reducing sugar. So glucose is a reducing sugar. Glucose is a reducing sugar because it reacts with these oxidizing agents. It gets oxidized, but it reduces the metal, the cation, to the solid metal. Now, what about ketones? What happens if you try to oxidize a ketone? Well, if you try to oxidize a ketone, you get no reaction. So what would happen, say, if we used a sugar that was a ketose? Such as, for example, fructose. If we reacted a sugar, such as fructose, we would expect no reaction on oxidation because it is a ketone, a ketose. What's interesting is if you react it with Tollen's reagent, you discover that fructose is a reducing sugar, and you do get a reaction. The key to this is the fact that this sugar can react with the base. Base can actually deprotonate the top CH2OH. And the reason it can deprotonate here is the presence of the carbonyl resonance stabilizes the anion. Okay. Now this guy can very quickly pick up a proton, but remember when base, there's no H plus around, so H2O would have to come in, and the reagent is dissolved in water, would have to come in, and it would grab a proton, and you'd get this. And what we've made here is an enediol intermediate. Now we learned about enols last semester. And enols, we learned were unstable and could tautomerize back to the keto form. So essentially what I'm showing you here is how this tautomerization took place. So we started with D-fructose, and the base could convert D-fructose to this enediol intermediate. So D-fructose can be converted to this enediol. Now, the whole process can happen again. I mean, I can deprotonate the OH, but if I deprotonate the same one, I just go backwards. If I deprotonate the OH on the top CHOH, so have base come in, I will get CH, actually let's just draw CHO minus double bonded to a COH, CH2OH down here, running out of room. That is resonance stabilized with the minus charge on the structure, and I get this. And you see we can have now water come in, and you can pull a proton off water. What's interesting is the chirality here will be scrambled at the carbanion. So you will produce two possible sugars. You will produce D-mannose, or you will produce D-glucose. Okay. So in base, via the enediol intermediate, D-fructose can convert to D-mannose and D-glucose. Now, D-mannose and D-glucose both have aldehyde groups, which can get oxidized. Hence, the D-fructose doesn't really get oxidized. It converts to D-mannose and D-glucose via this process of tautomerization. And D-mannose and D-glucose are what react. So D-fructose, a ketose, is a reducing sugar because it can convert in base. It can convert in base, and it can also do it in acid. It can convert in base to the aldose sugars. Now, every good reaction mechanism needs an interesting name, and this guy has a good name, actually a fascinating name. it is referred to as the DeBruyn van Eckenstein transformation. Now that is a name that will stick with you. DeBruyn van Eckenstein transformation. And all I expect you to know from this transformation is what I've drawn in red. And I'm going to left a few things out. I'll circle a couple more things in red. You need this. So D-fructose in base gives you the enediol intermediate. And the enediol intermediate, again, reacted in base, gives you D-mannose and D-glucose. So what I've circled in red is what you need to know and be able to draw. It is this that goes on and produces the CO2 minus, and hence in the oxidizing process you would get a CO2 minus at the top of D-mannose or a CO2 minus at the top of D-glucose. The D-fructose itself does not get oxidized. It is only when it converts to D-mannose and D-glucose. Well, there you have it. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you very much.